We will be going over the derivation of the compound interest formula for n compounds. Suppose you walk into a bank and deposit $50 and they provide an interest rate of 5%. Let's consider 0 years, 1 year, and 2 years. At 0 years, you will have $50. In 1 year, you will have $50 plus 5% more, which is 50 plus 50 times 0.05, which equals 52.5. In 2 years, you will have what you had the previous year, 52.5 plus 5% more of that, which is 52.5 plus 52.5 times 0.05, which equals 55.11. Now let's substitute these numbers with variables. We will replace the principal amount $50 with P, and we will substitute the rate 5% with R. We can factor out a P, which will result in P times 1 plus R. In 2 years, you will have what you had the previous year, P times 1 plus R plus the rate of that, resulting in P times 1 plus R plus P times 1 plus R times R. When you combine them, it equals P times 1 plus R times 1 plus R. Simplifying even further will equal P times 1 plus R squared. For year 3, you bring once again the previous amount, P times 1 plus R squared plus P times 1 plus R squared times R. This will simplify to P times 1 plus R cubed. You can see that the exponent represents the same number of years. Therefore, we can conclude that for t years, the equation will be P times 1 plus R to the t power. To accommodate for more compoundings per year, such as quarterly, monthly, or daily, we will let n be the number of compoundings per year and let t be the number of years. Then the rate per compounding is R over n. And the account balance after t years is A equals P times 1 plus R over n to the nt power. Before explaining the derivation of the compound interest formula for continuous compoundings, you must understand what constant E means. E is equal to 1 plus 1 over x to the x power as x gets really big. Constant E is considered the natural base. E is approximately 2.718. Now let's continue with the derivation for the continuous compounding. Suppose the number of compoundings n increase without bounds. The process approaches what is called continuous compounding. In the formula for continuous compounding per year, let m equals n over r. This results in A equals P times 1 plus R over n to the nt power. Now let's substitute mr for n. Then we simplify, and the r's cancel. By properties of exponents, we can break down the equation to this. This is where constant E comes into place. As m increases, 1 plus 1 over m to the m power nears E as m nears infinity. So we substitute E for 1 plus 1 over m to the m power. Now I will show you an example using the first formula. A equals P times 1 plus R over n to the power of nt. A total of $7,000 is invested at an annual interest rate of 6%. Find the amount after 5 years if compounded quarterly. P is equal to 7,000, R is equal to 0.06, n is equal to 4, t is equal to 5. A is equal to 7,000 times 1 plus 0.06 over 4 to the power of 4 times 5. A is equal to 7,000 times 1 plus 0.06 over 4 to the power of 20. When I plug this into the calculator, A is approximately 9,427 with 98 cents. Now I will show you an example using the second formula. A equals PE to the power of RT. A total of $5,000 is invested at an interest rate of 8%. Find the amount when compounded continuously for 10 years. P is equal to 5,000, R is equal to 0.08, T is equal to 10. A is equal to 5,000 E to the power of 0.08 times 10, which is 0.8. A is approximately 11,127.70.